Hey, hello. Welcome to lecture second of Introduction to CNN. I am Aryan Mungla. I hope you have watched the lecture one. So, let's get right into it. The first topic we'll covering today would be striated convolution. Now, what is striated convolution? You can basically understand that it is very simple concept in which we are taking more than one step in moving a filter. So let me show you how it works. So imagine this is a 7 by 7 uh, image and with a 3 by 3 filter. Now here we are defining a stride as 2. So what will happen in this is that this is like first we have applied a filter here like normally, which we have seen in the previous video. Now if we move the filter like in the normal scenario, what it should happen that it is moving by one place, but here it will move by two. So like normally you are expected to move from here to here, but now it has moved to two places because the stride is set as 2. So this is basic, the filter is moving with whatever the value of stride is being set. So other than from the default convolution, whenever we define a stride, it moves with that stride. So now it moved from here to here, then it moved to here. So and this will be computing the values as we explained it earlier, and here also it will be moving through two steps. So from here it didn't go to this sixth line, it go to directly this third row. So because stride is set as 2 here, so subsequently it will do all the computation, and this will be the result. So this is how a strided convolution work. Here we also have a formula to decide how this stride is working. So the formula is n plus 2p minus f upon s plus 1. So this is the same formula which you have seen in the previous slide when we were talking about padding. So now with here the n plus 2p minus f sub part of the formula is divided by s. So this will give us the right value which is being taken up there. And one more important point is that here we take the floor value of it. So I hope you understand that floor values, whenever we are getting a decimal value, we will be taking the floor integer, that is the integer within the matter. So here we are taking the floor of it, and basically this gives us how we are getting this the output kernel dimensions. So if we talk about summary of the convolution, so like we have an end-to-end image with convoluted with a f2 f filter. We can set padding, we can set stride, and this is basically a formula that can like compile the whole like all the key concepts, like n is the initial image number, p is the padding which you are putting in it, f is the filter size, s is the stride. So by using this you can get the output kernel size, so that will help you define and help you decide the architecture of the neural networks which you will be working upon. So let's now move to second topic, that is the convolution over volume. So in this topic we will be talking about how convolution is being done on a real RGB image. So let's move right into it. That yeah, now suppose this is a normal RGB image. RGB is red, green, blue. So any image, like let's suppose we have taken the height and width of the image as 6 into 6, and we are devising the channel as 3. So these are the number of channel here. This is the height, this is the width, and this is the number of channel. So in this, we can when always the channels of the input image, the input kernel, and the filter will be always same, because they will be help us in doing the convolution. So you can imagine that the filter here 3 by 3 can be imagined as a cuboid, right? And how you can imagine this is that we are convoluting on a particular RGB image, on a real life image which has these channel. We are putting this kernel, we are putting this particular filter kernel directly onto it, and we are convoluting among the three-dimensional space, that we are multiplying this by this by this by this subsequently, to make a resulting single 4 into 4 dimension output kernel. So that will help us reduce the dimension. So we will first place this cube uh, on the corresponding RGB image here, and here we can see that it is 3 into 3 into 3, that's 27 numbers will be computed in, and that's how we will compute these 27 numbers and convolute it with the input image, and thus we will get the first. So these all three layers will be convoluted, and that will give the first layer. Then we will move it by one, as we seen in the normal convolution. It will move by one, and we will get the second. Similarly, we move it by one, we will get the third, we will get the fourth, we move it down fifth. So this is how the whole convolution will work. So this is a very real life example on how we actually work with RGB images, and how we actually do all these operations on it. So the filter here, as you can see, it is RGB filter, in which let's suppose in the first we want to, so now we are taking an example, like suppose in the first case we want to detect vertical edges in a red color. So we have set the red filter, the filter that is corresponding for the red color, the computation which will be happening with the red color. We have set it to detect the vertical edges, because we want to, let's say we have an image and we want to know what are the vertical edges specifically of the red colored part. So as you remember from the previous lecture, these are the filters, like these are the decided filter which will help us decide the edge detection for the vertical edge. So if we convolute this, and we will keep green and blue will be zeros, all zeros. So this will help us identify what are the corresponding vertical edges in the red color. So like this we can maybe if we want to get the vertical edges on all of these, all of the red, green, blue, then we can set all of these in 1 and 1100 -1 -1. So we can set all three the same kernel, and this will give us the corresponding vertical edges for the whole images. So that's how you can experiment with different combination of the filters, and we can get our desired results. So as I was telling you, if we can cook this into all vertical edges, so this will give us the all the vertical edges in this whole image. Now we can also apply multiple filters into our image. So if we want to use multiple filters on a particular image, like we want to detect horizontal edges, diagonal edges, and vertical edges, and we want to do all of them, so we can also apply multiple filters on a particular image. So let's take this simple example, that in this 6 by 6 into 3 image, we are convoluting it with these two filters. That is, one is set for the vertical edge detection and one for horizontal edge detection, and that is resulting into two 4 into 4 images, and we can then combine these 4 into 4 images into so these will be two channels right now. So this 4 into 4 into 2, that will be the final image which with two filters apply. So that's how we can form this 4 into 4 by 2 cuboid. And the filter also have the same depth. So it make 4 into 4 into 3 with like k into 3. So like these filter numbers should be the same, the channel number in the filter and the input image should be same. That will make the one feature map, and then combining both of these feature map will result us into our final image that will be detecting both the vertical edges and the horizontal edges of the image. So this is one more thing. So yeah, so if we summarize this, so like the channels on the input image and the filter image should be same, that is 3 into 3, and these will result us into giving the feature map, that is n minus f plus 1, because here we are not using any padding or strides, so we are using the simplified version of the trick. And this NC will be the number of filters, the total number of filters which we'll be using. So here we are using two filters, so that's why we are getting the filter number as 2. So through this you can combine multiple filters into a single input image, and you can do much more things on it. So now we move forward to single layer of convolution. So now we are going to visualize how a single layer of a convolution network work. Okay, so yeah, let's suppose this is our main image, that is a 6 by 6 into 3 dimensional image. Here we are convoluting with two filters of 3 into 3 into 3 dimension, right? Now we are moving it forward with like we are convoluting it, and we are getting a 4 by 4 output kernel, as we have seen in the previous example also. Now suppose that we are talking in terms of code, like now we are writing, now in the next step we will be writing codes, and we want to imagine how a single layer of CNN works. So suppose this is our output kernel. We maybe add a bias on it, a real number bias on it, and we are making it out of a ReLU network. We are passing it through a ReLU activation function, and then we are getting our final output kernel. Similarly here we are adding a bias of B2 along with our ReLU activation function, and we are getting a 4 into 4 output kernel, and combining both of these will result into 4 into 4 by 2 as we should, because we are using multiple filters here. Now I want you to imagine like how this like I hope you remember this simple, the basic neural network equation, that is z is equal to w1 a0 plus b1. So now I will help you imagine how we can like how we can relate these mathematical terms to how we are in this scenario of this computer CNN network. So you can imagine that a0, that is activation, the zeroth activation function, is the input image here, that is convoluted with the weight. The weight here is the filter. So filter can be imagined as a weight, and while at the same time this input kernel image can be imagined as an activation function. So these weight can be convoluted with the activation function here, and the both of them combined will be resulting into our output image that we have seen here, the w1 a0. So this will be summarizing to this particular manner. And as we seen, this is the added bias here, so we are adding bias along with the ReLU function. So like this particular fraction, the like the blue like encircling the blue rectangle here, is basically the z1 here. So we got the z1, and now for the activation function we pass it through an activation function of g. Here we have selected as it as ReLU. So when we pass it through ReLU, the whole combined thing is the a1, and we are combining both of them, so this will result into a1. And here, so you can see it as this a0, that is the initial activation function of 6 by 6 into 3 image, is being convoluted into an a1 activation function in the next step, which is now 4 into 4 by 2. So there is a good dimension reduction here, and maybe we can like imagine it as I told you in the previous, to just clarify that we can increase any amount of filters, and those will result into that much detection, and like however we want. So if, like, let's say if we choose not to go forward with 2 filters but with 10 filters, then the resulting dimension will be simply 4 into 4 into 10. So how many filters we select, it will directly like affect our output dimensions. So let's now to understand this concept properly, let's now imagine an example here. So if you have 10 filters, that is 3 into 3 by 3 dimension in one layer of neural network, how many parameter does that layer have? So I want you to pause the video right now, and I want you to first think of an answer and then continue with the solution. I hope you have thought of some answer. So now I will get right into it. So this 3 into 3 into 3 filter will be itself into 27 parameter, plus there will be a bias that will be resulting into a total of 28 parameters for one filter. Now we are moving it for the 10 filters, so these 28 into 10 will be simply 280 parameters will be there in that particular layer. And it as we can see here, it doesn't depend on the input image. So the number of parameter are directly correlated to the number of filters which we are using, number and the dimension of the filter we are using. It has no directly dependence on the input image. Okay, so now like to just summarize what we have worked upon is that like if there is a layer L in a convolution layer, so FL will be the filter size here, PL will be the padding, SL will be the stride of the convolution layer. The input can be imagined as height, width, and channel. The number of height, number of dimension of like width and the channel, with like layer L minus 1. The previous layer will be the input, and the output will be the current layer. We can like as I told you, we can identify the output layer, that is the output kernel, the final kernel dimensions, with the help of this formula in like nh plus 2 n plus 2p minus s by s plus 1. As I told you, this is a very simple trick to get to know. And again, I'm mentioning this explicitly, that here we are taking floor of the values. Okay, whenever you are stuck in a situation of decimal, so you have to take the floor of the values. NC is a number of filters. Each filter is basically FL into FL into NC L minus 1. That is the number of input dimension. So this and the input image, these both of these, as I told you multiple times, these should be same for the convolution operation. And the activation is NH, NW, NC. And the final like if we are taking upon a array of a different convolution image, so the activation number will be m with the number of examples taken here. And the weight would be a filter FL into FL plus NC into NC. So this will be the basic filter, as I told you in the previous layer, the previous slide, that the weights would be, the parameters would be totally dependent on the filters. So we are taking the filter more dimension, and FL in this whole here all the filters along with the number of filters in the layer. So we have taken 2 filters, 10 filters. So in the previous example, we have taken 10 filters of 3 into 3 into 3. So these will be the that will be deciding the weight of that. And the bias of this will be the normal, the number of filter minus whatever the filter we have decided. So this will decide the bias of it. And again, this whole can be taken as NC, and we can imagine it in this part. So this is the basic summary of the notations which we'll be using throughout our journey, in which we, whenever we are writing a convolution network or whenever we are deciding convolution layer, so these are all the basic essential basic parts which are needed. So the filter, padding, stride, what is the filter, activation, weight, bias. So I've helped you imagine these mathematical computation with the visual of how each part is working. So I hope this will help you get a better understanding of the uh, this concept of the convolution neural networks. And I hope you have grasp the concepts here. And let's meet in the next lecture. Thank you.